Hi everyone, welcome to my channel. In this video we're going to cover Boolean algebra. In the last videos we covered the binary number system. We investigated the AND, OR, and NOT logic gates, their symbols, and the associated Boolean algebra that describes their operation. And we covered the NAND, NOR logic gates. Now, we sort of touched on this, but basically Boolean algebra can be used to analyze a logic circuit and express its operation mathematically. Now, once the Boolean expression for a logic circuit has been obtained, it may often be reduced to a simpler form using Boolean algebra. And that brings us to the most important application of Boolean algebra. And that is the simplification of logic circuits. And what we'll find is that once we have obtained the Boolean algebra, the expression for a logic circuit, we can often reduce that expression to a simpler form using Boolean algebra. We're going to achieve this simplification by using Boolean theorems. Which we will define in this video. Now, the first group of Boolean theorems we're going to define are single variable theorems. We're only going to be dealing with one variable, x, and x will be able to equal 0, or x will be able to equal 1. So these first theorems are pretty straightforward, but you can prove them just by plugging in for x equal to 0 and x equal to 1. So we will show the theorem and then the associated logic diagram for that theorem. So theorem number 1 states that x and a 0 will equal 0. And the logic diagram will show that an AND gate with two inputs, where one input is a variable x and the other input is tied to 0, is constantly 0, we will find that the output will always be 0. The next theorem, x and a 1 will equal x. And here's the logic diagram expressing that, where we have x, the variable input, can be 1 or 0, and the other input is constantly tied to a 1. The output will be x. Now you can see here an AND operation is similar to ordinary multiplication, where anything multiplied by 0 will always be 0, and anything multiplied by 1 in this case will be x, whatever that variable is. So if x is a 1, the output will be a 1. If x is a 0, the output will be a 0 for the logic operation AND. Third, we have x and x will equal x. and we express that as another AND gate. And in this case, both inputs are equal, so they are tied together. So if we have an X on the input, we will see that the output will always be X. So if we AND, if X is 0, two ANDs together, we know that the output of an AND gate is only high when both inputs are high. So when X is 0, the output will be 0, and when X is 1, the output will be 1. Number 4, X and X naught will equal 0. So if we have an input X and the other input has an inverter on it, or a NOT gate, this will always be 0, because whatever X is, X naught will be opposite. So if we have X equal to 1, X naught will be 0. And whenever any of the inputs on an AND gate is 0, the output will be 0. Next, we have 4 theorems associated with OR gates. So we continue with Theorem 5, which states that X OR together with 0 will equal X. And the associated diagram is an OR gate. And we have one input that has the variable X, and the other input is always tied to 0. That output will be X. Next we have Theorem 6, which is X ORed with 1 will always equal 1. So we have X and the other input tied to 1. That will always be a 1. Theorem 7, we have X ORed with X. So both inputs are tied together. This will, of course, equal X. We have Theorem 8, which is X ORed with X naught will always equal 1. And the associated diagram, we have X, and then of course the other input will be the opposite, so we have an inverter, and that'll equal 1. Next we will define multivariable theorems. Before covering multivariable theorems, we want to point out that with the single variable theorems, X can also represent an expression. So for instance, X could equal A B naught. So if we then had A B naught and together with A B naught, and that had an inverter sign over it, that would equal 0, because if we had X equal to A B naught, this is similar to X and X naught, which we know is 0. So in the single variable theorems, X can actually represent an expression, not just a single term. So this group of theorems are multivariable theorems. The first one is x or y is equal to y or x. Number 10, x and y is equal to y and x. These two theorems are the commutative laws. Which states that the order in which we add or multiply two variables is unimportant. So the order in which we add or multiply two variables is unimportant. The next two are the associative laws. So we have number 11, which states that x or y or z is equal to x or y or z, grouped differently. And this is also equal to x or y or z. And 12, we have x and y and z grouped this way is equal to x or y or z, which is equal to x, y, z. And this is the associative law. And the associative law states that we can group terms of a sum or a product any way we want. We can group the terms of a sum or product any way we want. The next theorem is the distributive law. So theorem 13 states that x and y or z is equal to xy or xz. This is the distributive law, which states an expression can be expanded by multiplying term by term. And this also indicates that we can factor an expression. So this states that an expression can be expanded by multiplying term by term. So what we do is we multiply this and then we multiply by this. But this also indicates that we can factor. So if we start off with xy or xz. This is equal to x. We can factor out x is the common variable of these two terms, leaving us with y or z. Theorem 14 states that x or xy is equal to x. These two are equivalent. And theorem 15 states that x or x naught y is equal to x or y. So using these theorems, let's simplify a Boolean expression. So if we start off with y equal to a b naught d, and that's OR together with a b naught d naught, we can see we have two terms and they have a b naught in common. We have it there and there. So we can factor that out. So if we factor out a b naught, this becomes d or d naught. So here we use the distributive law to factor out a common term. So now this here is similar to x ORed with x naught. And we know, according to this theorem, x ORed with x naught will always equal 1. So this becomes a b naught and 1. So y is equal to a b naught. So let's simplify another expression. If we start off with z equal to a naught ORed with b, and that's AND with a or b naught. We want to expand this expression, multiplying term by term, so we have a naught a, and then we multiply a naught by b naught, so we have OR a naught b naught. And then here we multiply, we have b and a, and here we have, that's OR together with b naught. So we can see here that a and a naught is equal to 0, and b and b naught is equal to 0. So this is 0 ORed with a naught b naught, or together with b a, or together with 0, and this is just equal to a naught b naught, or together with b and a. So Boolean algebra and Boolean theorems can be used to simplify a Boolean expression. Here we have a logic circuit diagram, and we have the Boolean expression for the output x. This expression can be simplified to x equal to a, b, c naught. And the logic circuit diagram for this expression would be a single AND gate with 3 inputs. We have A, B, and C, which has an inverter on it. and the output x would equal a, b, c naught. These two equations here are equivalent, and these two logic diagrams or circuits are equivalent. So it's easier to implement the simplified Boolean expression and its associated circuit. So this single gate, this circuit here, has less gates and fewer connections. So it would cost less to implement. So we can see here that the most important application of Boolean algebra is the simplification of logic circuits. Now we haven't covered this yet, but if you look, we have an inverter sign here that is over two terms. Two of the most important theorems in Boolean algebra are De Morgan's theorems. And these theorems help us to deal with large inverter signs that go over more than one term. And we will cover that in the next video. So I hope you found this video interesting. Feel free to like, comment, and/or subscribe. And thanks for watching.